Hello, welcome to Smart Samaan's newly launched gate driver board. This board is a standalone independent gate driver along with PWM generation for the single phase and three phase inverters, and it can generate up to four independent 10 to 15 hertz 10 to 15 volts PWM signals. It has an option to apply either the onboard PWM generation or the PWM generation from any external microcontroller. It incorporates a high-speed SD controller to generate the onboard PWM pulses. The PWM select header can be used to select between the options of onboard PWM from the onboard microcontroller or the external PWM from any external microcontroller. Okay, so the connectors CN1 to CN4 generate the four output PWM pulses based on the independent power supplies. The board has the option of four general purpose IOs from PB0 to PB2 and PD4, and these IOs generate 1 Hz, 5 Hz, 10 Hz and 50 Hz logic waveforms. So it means these logic waveforms are directly coming from the microcontroller to these pins, and anyone using this type of PWM, logic PWM, has to use the gate driver circuit externally. So the connector CN1 to CN4, they generate the PWM pulses based on the onboard gate driver circuits. Okay, so a user can use the smart gate driver app to program the board for the desired PWM type by using a USB Type-C cable and a computer. Now let's install the smart gate driver software. So here is the setup. Follow the steps to install it, and here we go. So the software has been installed. Now let's launch the software, and this is the welcome screen for the smart gate driver manager, and here you will see the ports by clicking the refresh button. So if you have connected the board with the computer and you click the refresh button, you will see a port appearing here. So for this our case, we have connected the smart gate driver board with the computer through a USB Type-C cable. So we are seeing COM3 here. So now select SGT type, which is 4 channel for now, and click open to open the board. So on this screen, we can select different parameters and type of PWM signals to be generated by the smart gate driver board. So let's start with the complementary mode and then select the PWM as the square PWM. So here these things are disabled because they are not required for the square PWM type. So only the fundamental frequency is needed. So a user can enter any frequency within a given range or within the provided range to generate the PWM. So for example, let's generate a fundamental frequency of 50 Hz square wave by clicking the program button. So here it can be seen that the gate driver board has been programmed successfully. Okay, so now let's go to the logic analyzer and see the outputs. So the first four PWMs here are the complementary PWMs being coming from the output ports connector CN1 to CN4, and the last four are the logic waveforms on the general purpose IOs, right? So right now we are only interested in the first four waveforms. So we can see that they have exactly 50 Hz with 50% duty cycle, and they are in complementary mode. So first two are in the same phase and the second two are in the same phase but opposite to the first two. Alright, so now let's change the frequency to 100 Hz and try to program it again. Here we go. So let's verify it. So here you can see that the frequency has been increased. You can measure it as well. So here is the frequency of 100 Hertz. Alright, now let's change the PWM type to quasi-square wave with a delay angle of 20 degrees, let's suppose. So here is the definition for the delay angle. So this is the type of output that you will get when you are using a single phase inverter and providing these 4 pulses to that inverter. Alright, so let's program it. So here we have programmed the board. Now let's check the output. Here you can see that this is the quasi-square output wave and it is generating exactly 100 Hertz with the delay angle on both sides. Alright, so now let's change the delay angle to 45 and program again. So here we go. So now you can see that the delay angle is higher than the previous value. So the high time of the pulses has been decreased as compared to the previous case and the frequency is still 100 Hz. Alright, so now let's select another type of PWM, that is ANDed PWM, and by using this type of PWM you will be going to get this type of output voltage on the inverter. So for this case we have 100 Hz and then let's suppose the carrier frequency is 1 kilohertz and the modulation index for this ANDed PWM is, let's suppose, 50 Hz. Alright, so let's program it. Here we can see that this is the ANDed PWM output with a frequency, fundamental frequency of 100 Hz and the high frequency, that is the carrier frequency, as 1 kilohertz. Now let's change the modulation index to 10%. So in that case we can see that the width of the pulses has been decreased and it is only 10% high and 90% low. Alright, so now let's try another type of PWM, that is unipolar sine PWM. So by using this type of PWM, the expected output of the inverter will be like this one. Alright, so let's change the modulation index to, let's suppose, 100%. Suppose we are generating 50% duty cycle, 50% fundamental frequency and carrier frequency of 500 Hz. So if we mistakenly selected 500 kilohertz, we can get an error because the allowed range for the carrier frequency is 0.5 kilohertz to 20 kilohertz. So let's suppose we select 500 hertz and program it. So let's wait for the program. Here we go. Okay, so in this case you can see that we are going to get unipolar sine PWM pulses. Alright, so let's verify it by using a cursor. So here we go. So it is exactly 50%, right? Okay, so now let's change the carrier frequency to 20 kilohertz. So in this case, let's reprogram it. So now let's check the output. Okay, so here is the output PWM pulses having a frequency of 20 kilohertz, and if we try to zoom in the waveforms we can see that it is exactly a unipolar sine PWM. Okay, so now let's apply the PWM type as bipolar sine PWM with the frequency, fundamental frequency of 50 Hz and carrier frequency of 500 Hz. Alright, so if we program it, we will be able to see the output pulses as the bipolar PWM pulses. Here we can check the time of the pulses as it is approximately 20 milliseconds, which is 50 hertz. Okay, so next we will move towards the independent PWM, where we can see that there are two different type of channels available, where channel 1 and channel 2 means the PWM 1 and PWM 2, they can be programmed using a single frequency but with variable duty cycles. Similarly, we can use channel 3 and 4 to have a 50% duty cycle but different frequencies for the two PWM pulses, for the last two PWM pulses. Okay, so you can see the information here as well. Okay, so let's select the frequency for channel 1 and 2 as 50 Hz, with the duty cycle of the first PWM as 10% and the duty cycle of second PWM as 20%, and let's program it. Now you will be able to see that we are only going to get first two PWM pulses, and keep in mind that they are aligned to the sides of the reference. So it means the first PWM is left aligned and the second PWM is right aligned. So the first PWM is of 10% duty cycle with 50 Hz frequency. Second one is the 20% duty cycle with the 50 Hz frequency. Alright, so if we select channel 3 and 4 as well and apply the frequency of 10 Hz and 40 Hz, and let's program it. Now we will be able to see the third and fourth PWMs as well. So here you go. Here we can see that the third PWM is of 10 Hz because we had selected 10 Hz, and fourth one is 40 Hz, which is exactly 40 Hz here. Okay, now let's verify the logic waveforms on the general purpose IOs. So let me rerun the simulation. So the logic waveforms start from channel 4 on the logic analyzer and go up to channel 7. So this channel 4 is connected to PB0, which generates 1 Hz frequency. Then this channel 5 is connected to the PB1, which generates 5 Hz. Then channel 6 generates 10 Hz and it is connected to PB2. And last one is channel 7, that is connected to PD4 and it generates 50 Hz waveform. So let's wait for the complete cycle of this 1 Hz to verify it. So here we go. So let me stop the simulation and verify. So here we can see that it is 0.99 Hz, which is very close to 1, or you can see the time, that is 1.00791 seconds. Then this is the second one, that is 4.96 Hz, and then this is the third one that generates 9.92 Hz PWM, and last one is the 49.6 Hz, which is close to 50 Hz, and that is generated on the PD4. Okay, so these logic waveforms are approximately same as the input as the given frequency. Now let's test the PWM waveforms on a real single phase inverter. So first of all, let's test this 50 Hz PWM. So here you can see the result on the right side on the oscilloscope. Now let's change the frequency to 100 Hz and reprogram the board, and here you go. So it is exactly of 100 Hz frequency and it is a purely square wave. Now for the quasi square wave, we can change the frequency to 50 Hz again and change the delay angle to 20 degrees and program it. So now you can see that this is the output of a quasi square wave inverter. By changing the delay angle to 45, we can see that the output is changed accordingly. Now let's test the AND PWM, where the fundamental frequency is 50 and carrier frequency is 1 kilohertz. And here you go. So for this case, modulation index is 50%. Let's change the fundamental frequency to 500 hertz, sorry, carrier frequency to 500 hertz, but you can see that we get an error because it is out of the range. So keep it to 1 kilohertz and change the modulation index to 10%. So here you go. You can see that it is an AND PWM waveform. Now to test the unipolar sine PWM, let's change the carrier frequency to 500 Hz and the modulation index to 70% and program it. So let's wait for the programming. And here you go. So this is the output of a unipolar sine PWM inverter. Change the modulation index to 100 Hz, 100%. And in this case, you can see that this is the output. And finally, let's change the PWM to bipolar sine PWM. Keep the same parameters, but the modulation index as 70% and program it. So here is the output of the bipolar sine PWM inverter with 70% duty modulation or duty cycle. So here the modulation index is changed to 100% to see the output. So here it is. Alright, so this was about the functioning of smart gate driver board. So on the screen you can see the smart gate driver board with the inputs and output peripherals and ports mentioned on the diagram. So for more information about each of the input and output peripheral and pins, you can consult to the datasheet of the board, which is available on our website. So that's all about this video. So thank you so much.